So in the last session, we learned how to find the cosine of a sum of two angles that we already know, or a difference of two angles that we already know. So let's just say that we know angle A and angle B, then we were able to find cosine of A plus B, or cosine of A minus B. Well, now we're going to derive the formulas for being able to do the same thing for sine and tangent of a sum or difference of two angles. Now you can remember that in order to derive the formula for cosine of A minus B, we drew a diagram by locating in the second quadrant an angle A and the first quadrant an angle B, and we ended up finding where A minus B would be, and we went through the derivation of that formula. And the formula we came up with was involving sine and cosine of A and B separately. You might also remember that sine and cosine are cofunctions, and so that means that if we take sine of some angle, then that will always be equal to cosine of the complementary angle in the right triangle, so 90 minus theta. So we can use that fact in order to create the sum formula without drawing a diagram, without going through the proof like we did for cosine of A minus B. We could do the same thing for sine of A plus B. So this becomes cosine of 90 degrees minus the quantity of A plus B. Now we notice that this is a difference of two angles. And so since it's cosine of a difference, we should be able to use this formula right here. But if I were to use that formula, then A plus B would come in the location of where this angle was in the formula. And I don't want a formula involving a sum of two angles. So what we're going to do instead is we're going to change this form by distributing that negative. And we're now going to rewrite this as cosine of the first angle, which would be 90 degrees minus A. So we're just redistributing this by the associative property, minus the angle B. And so now that we see this, we're going to be able to use the difference formula for cosine, which is cosine of the first angle, 90 minus A, times cosine of the second angle, plus sine of the first angle, which is sine of 90 degrees minus A, and sine of the second angle. But now you should recognize the cosine of 90 degrees minus A and sine of 90 degrees minus A are cofunction identities. So that means that sine of A plus B can be rewritten in a very similar way to what cosine of a sum and difference was, except for notice that cosine of 90 degrees minus A is sine of A. And we keep the cosine of B, drop that down, plus, and now we see that sine of 90 degrees minus A is cosine of A times sine of B. And this is the formula for sine of a sum. So you can see that it looks somewhat similar to the cosine sum and difference formulas, but the one thing to note here is that for cosine, the first term has both cosines and the second term has both sines. While for sine of a sum, now we realize that it has one of each in each term. Secondly, you might remember that for cosine of A plus B and cosine of A minus B, the sign was different than what you were referring to in the difference. While for sine, notice that the sign is the same. And so just a couple of ways to memorize this and recognize the patterns. But notice that they look very similar. They're still involving sine of A, cosine of A, sine of B, and cosine of B. It's just a different format for each one of them. Now we can derive the opposite formula for sine in the exact same way we derived the second formula for cosine by thinking about sine of A minus B as being sine of A plus negative B. Because now I have another sum formula, which will allow me to rewrite the formula here as sine of angle A cosine of the other angle plus cosine of angle A times sine of the other angle, which is negative B. So now by our cofunction, or I'm sorry, by our even odd identities, keeping in mind that cosine is an even function and sine is an odd function, then we're able to now derive the formula for sine of A minus B by just realizing that cosine of negative B is the same as cosine B. So I can just drop the negative sign and that becomes sine A cosine B. But now for sine of negative B, I know that that's an odd function, so I'm going to have to pull out that negative. So now that becomes minus sine of A cosine of B. And notice again how the formula is exactly the same as the sum, except for the sign between the terms. So if sine of A plus B has a plus sign, then sine of A minus B has a minus sign. So now we've got the formulas for sine and cosine of a sum and difference. So let's do an example. Pi over 12 is not a standard angle from our unit circle, but I do know that pi over 12 happens halfway in between the pi over 6 angles. And so I can think of 7 pi over 12 in a couple of different ways, and it just depends on how we choose to approach this problem. I could think of 7 pi over 12 as, well, a difference of two angles that both have a denominator of 12. Or I could think about them as a sum of two angles that both have a denominator of 12. And there's an infinite number of ways to actually represent this angle. But for instance, 7 is 9 minus 12, or I'm sorry, 9 minus 2. And so that's one way that I could maybe represent this, because 9 pi over 12 simplifies to 3 pi over 4, which is an angle on our unit circle. And I know that 2 pi over 12 simplifies to pi over 6, which is also an angle on our unit circle. So I could rewrite sine of 7 pi over 12 as sine of the difference of those two angles. Or I could try this in a different way, and I could think about this as being something like 4 pi over 12 plus 3 pi over 12. And the reason why I might do that is that these are also both on the unit circle. Pi over 3 is on our unit circle, and pi over 4 is on our unit circle. So I could think about 7 pi over 12 as a sum of two angles. Now these aren't the only ones. I mean, I could also represent 7 pi over 12 as 5 pi over 12 plus 2 pi over 12. But notice that this one here wouldn't work, because even though 2 pi over 12 simplifies to become pi over 6, 5 pi over 12 is not a common angle on our unit circle. So that would be a poor choice of sum or difference, since our whole goal is to create angles that we can actually evaluate individually. All right. So let's just pick one of these. I'm going to pick the one that looks easier. So in this case right here, I would pick pi over 3 plus pi over 4. So why don't we now evaluate to find that sine of 7 pi over 12 is the same as sine of pi over 3 plus pi over 4. And now by using our sum formula for sine, that becomes sine of the first, cosine of the second, since it's one of each type of function. And the sign is the same, so I know that this is going to be addition. And now I get cosine of the first and sine of the second. And now that we have that whole expression, you could see that all I'm doing is evaluating the x and y coordinates at each of those individual points. And so notice that this becomes sine of pi over 3. Keep in mind, pi over 3 is the steep angle, so the y coordinate is root 3 over 2, times the x coordinate of pi over 4, which is root 2 over 2, plus the x coordinate of pi over 3, which is 1/2, times the y coordinate of pi over 4, which is also root 2 over 2. And therefore, if I add those two angles together, which both have a denominator of 4, then that just becomes the sum of the square root of 6 and the square root of 2 over 4. And so this here is our exact value for sine of the sum of these two angles, which is sine of an angle that we didn't know prior to this on our unit circle. So with the sum and difference formulas, we're now able to find some other trigonometric function values, even though they might not be pi over 6, pi over 3, or pi over 4 angles. We've already found the formulas for sine of a sum, cosine of a sum, sine of a difference, and cosine of a difference. We can now use those formulas, since we know tangent of theta is equal to sine theta over cosine theta by the quotient identity. We can use that fact in order to find a new formula for tangent of a sum. So if I just make the numerator the sum formula for sine, and the denominator the sum formula for cosine, then this technically is the formula for tangent of a plus b. But notice that I would have to evaluate 4 different quantities and divide it by 4 of those same quantities. That means I'd have to plug in 8 different quantities from our unit circle, and that could be really tedious. And so instead, what we're going to do is we're going to try to do something here to turn all of these terms back into tangent. Okay, so there's a little trick here, and I'm going to show you how this is, how we can remember how to do this. But notice that we're going to basically divide all of these terms by something that's going to cause them to turn into tangents. So think about this. If sine of a is in the numerator of a fraction, then that would mean that I would have to divide by a cosine of a in order to turn that term into a tangent. But if I do that, then that means I need to divide everything by cosine of a. Okay, so that's great, but notice that not all of the terms will now be tangent. So we should see that this term right here will turn into a tangent, but I'll still have an extra cosine. This term right here, at least, will cancel the cosine, which is nice, but I'll still be left with a sine. This term would cancel a cosine, but I'd still be left with a cosine. And this term will, in fact, turn into a tangent. But how can I get rid of the other terms? So why don't we now also think that if this numerator has a sine, that I could divide that by cosine of b, and that will now become a tangent. But that would mean that I'd have to divide everything by a cosine of b. And hopefully you're recognizing that a few things are going to cancel and a few things are going to turn into tangents. So cosine of b here will cancel. Cosine of b here cancels. But now each of these terms are going to turn into tangent of b, which means that we have a new formula for tangent of a plus b that only involves tangents. And so that's going to become tangent of a plus tangent of b. So the numerator appears that all I did was distributed that tangent. Even though that's not really what we did, it's something helpful to help you remember. Divided by, and now we see the numerator has a term that completely canceled, which means that that's simply 1. The denominator will have the opposite sign of the numerator. And now all that's left for the last term is the product of tangent A and tangent B. So now instead of dealing with the quotient of sine of a plus b and cosine of a plus b, we really only have to evaluate tangent of a and b separately and plug them into 4 different locations here. So this is the sum formula for tangent. And in a very similar way, we could actually derive the same thing for a tangent of a minus b. So by thinking the tangent of a minus b is tangent of a plus the opposite of b, That just means that we can plug in tangent of A. And for the second term, now it's going to be tangent of negative B divided by still 1 minus, and now it's the product of tangent of A and tangent of negative B. But this is where we look at our negative angle and realize that tangent is an odd function, which means that I'm going to pull out that negative and change the sign, which means that we now have our new formula for tangent of A minus B, which looks exactly the same as our sum formula. The only difference is that now I have tangent of A minus tangent of B. So the sign in the numerator changed. And finally, on the denominator, the negative from here multiplied by the negative from here means that that sign becomes 1 plus tangent of A tangent of B. And so both of the formulas, again, just like those formulas for sine of a sum and sine of a difference, or for cosine of a sum and cosine of a difference, they're the same formula. The only difference is the signs. So if we remember the formulas in this way, that the numerator is just the same sign, while the denominator is the opposite sign, that's going to be the same no matter whether or not we deal with a sum or a difference. Look at an identity involving tangent of a sum and difference. So first of all, when dealing with an identity, we always try to start with the side that it looks like there's more to do. So there's a more lengthy way to do this identity, and there's an easier way, and I'll show the easier way at the very end. But the first thing you might notice is anytime you see a sum of two angles, it's best to go ahead and use an identity to separate those into single angles rather than a sum. So why don't we go ahead and take this tangent of x plus y, and also this tangent of x plus y, and as we rewrite this, just change those into the formula. So I know the tangent of x plus y is going to be tangent of x plus tangent of y over 1 minus tangent x tangent y minus tangent y. So let's do that in a different color here. So we've got minus our original tangent y. And that's all divided by 1 plus, but now we're going to rewrite again tangent of x plus y as tangent of x plus tangent of y. And that's divided by 1 minus their product. 1 minus tan x tan y. And that's still going to be multiplied by tangent y. So that, again, doesn't look anything like tangent x. So what this starts to imply to me is that if this side right here is going to turn into tangent x, then there's going to be a lot of things that have to start canceling. All right. So what we're going to do now is recognize that we've got some complex fractions. So I'm going to multiply everything by the common denominator of 1 minus tan x tan y and 1 minus tan x tan y. Because what that'll do is it'll eliminate the complex fractions. So let's multiply by 1 minus tan x tan y. So this is an algebraic skill, right, that we can eliminate a complex fraction by just multiplying by the denominator. All right, well, if we do that, we've got to keep in mind here that there are actually 2 terms in the numerator and 2 terms in the denominator. So we're actually going to have to distribute this not only to the terms involving the fraction, which is going to cancel the denominator, but also to the second term. And same thing here, we're going to have to multiply this to the term that has that fraction, but also to the 1. So now the numerator becomes tan x plus tan y. Okay, and that's the first term, minus, and now we're going to have to multiply tangent y times 1 minus tan x tan y. Now, even though, again, it looks relatively complicated as a fraction, you just have to be patient and recognize that if this is going to be verified, things will cancel. And so we have 1 minus tan x tan y in the denominator because I had to multiply it by 1. But now, over here, this denominator cancels, leaving me with simply tan x plus tan y times tan y. And now if I'm going to be able to start canceling anything, we're going to have to start seeing some things cancel, or some things cancel after distributing. So why don't we get rid of all the parentheses, and this gives us tangent x plus tangent y minus tangent y, and look at that, one of the terms is canceling. And now we have plus tangent x times tangent squared y. Keep in mind when you multiply a trig function by itself, the exponent goes above the symbol of tan, okay? Divided by, and now let's go ahead and write this out. We get 1 minus tan x tan y. And now in the denominator, when I distribute the fraction, I get plus tangent x tangent y plus tangent squared y. All right, well, this is great because some things are starting to cancel. I see positive tan y cancels with negative tan y. I see that negative tan x tan y cancels with the positive tan x tan y. And so if you look in the numerator, I see two terms. I see tangent x plus tangent x times tan squared y. And in the denominator, I see 1 plus tangent squared y. Now again, this is where I'm keeping track of what my end goal is. My goal is to get tangent x, which means that I should be able to have no fraction left. This is a fraction on the left. I still have a fraction here, but if it's going to become tangent x, the fraction will have to cancel, which means that if you take a look at tan x on the numerator, there's a tangent x in both terms. So I could factor that out in the numerator to get 1 plus tangent squared y. And notice what's on the denominator, 1 plus tangent squared y. And that is how the fraction cancels. 1 plus tan squared y cancels, which leaves me with tangent x like I was expecting to get. So keep in mind, the answer is not tangent x. The answer is the process you took in order to get to tangent x. So it was, first of all, just using the sum formula for tangent. But once we did that, notice that it was a process of algebra to eliminate the complex fraction, another process of algebra where we distributed, another process of algebra where we distributed, another process of algebra where we factored, and finally canceled a common factor. So after we ended up doing the identity here, everything else was a process of algebra. Now that was the hard way. Let's take a look at the easier way. You might notice that the left side already looks like a sum formula. So if I look at this right here, this tangent of x plus y minus tan y, the whole left side, I'll bring that right down here. Instead of converting each of these quantities here into their formulas, okay, or into the sum formula for tangent, what we could have done instead is recognize that this kind of looks like A, and this looks like B, and this looks like A, and this looks like B. And so that looks like tangent A minus tangent B over 1 plus tan A tan B, which is actually the form of tangent of A minus B. So we could directly replace each of, or this whole formula with the fact that this simplifies to tangent of A minus B, but notice that A is x plus y, minus B, which is y. And sure enough, notice how it simplifies automatically to tangent x. So notice that either one of those proofs would have been acceptable, because when we're verifying an identity, you do whatever you can in order to get the other side to show up. Sometimes you recognize right away that this could be simplified to something else, like tangent of a difference. But let's say you don't know that, then you resort to trying something else. Let's make this here a sum formula, and let's make this here a sum formula. And although it took a lot more time and a lot more work, we still recognize that it got us to the same exact point either way. So now after these two lessons, we can now find the sine, cosine, or tangent of a sum of two angles or a difference of two angles, assuming that we already know the values of those two angles.